Okay, hi. Uh, Welcome to International Institute of Non-Destructive Testing. So today we are going to discuss here magnetic particle testing, and today's now our topic is on conductor, because in central conductor we are using conductor, that bar we are using to pass the current. Okay, so we are going to do now detailed study about that conductor. Okay, now see, uh, let's see this diagram of conductor, the little drawing here. Now this is the conductor. Now this horizontal axis represent the distance from center of conductor here, and this vertical axis it will give the magnetic field. Now see, if we are applying current here, okay, if we are applying current here to this non-magnetic conductor, then magnetic field increased, and here we are getting maximum, and now we are coming down here, and that maximum field we are getting at surface of conductor. Okay, means what? Whenever we are suppose we are applying current to conductor, non-magnetic conductor, then magnetic field will be maximum at surface of conductor. But you see here very carefully, outside, just outside diameter of conductor, just outside surface of conductor, the field is reduced here. So when direct current is passed directly through a solid non-magnetic conductor such as a copper bar, okay, such as copper bar, the following can be observed. The magnetic field strength varies from zero at the center to maximum at the surface. The field strength outside the conductor diminishes with distance from the central conductor center. So these are the things we saw there. Now here one more change is here, instead of non-magnetic, here is magnetic conductor. Now see, again the magnetic field is increased, and we are getting here maximum. And this maximum fields we are getting at outside surface of conductor, OD of conductor. But after outside surface, just field reduces. Hmm. So distribution of direct current magnetic field within the magnetic article can be illustrated graphically as shown this diagram. Now see, the flux density increases evenly from zero until it reaches peak strength at the center. Because of the permeability of steel, the field strength is greater within magnetic conductor as compared to non-magnetic conductor. Means if you are applying current to a non-magnetic conductor, field strength is less within a conductor as compared to magnetic conductor, because if we are applying current to a magnetic conductor, because of permeability the magnetic field will be higher within the conductor. And that is, I'm not saying outside the conductor. Outside the conductor, uh, about the same field, not exactly but about same field for magnetic as well as non-magnetic conductor, because outside field depends on permeability of outside media. Now outside media is their air, so outside field it depends upon permeability of air. So for in both magnetic and non-magnetic case, the magnetic field available in air, that depends upon permeability of air. So flux density drops rapidly just outside the surface of steel bar. The field strength outside a solid conductor is the same with either magnetic or non-magnetic conductor. Now instead of solid, we are taking here hollow conductor. Now you see the field at ID is zero, and again here increased, and where we are getting maximum at OD, means at outer diameter we are getting a maximum field, and now after the outside diameter field again reduced because of permeability of air. Now permeability is again a factor in determining field strength. If the outside diameter, the current flow are identical when comparing a solid and hollow conductor, the field strength will be the same. Means if you are using solid conductor or hollow conductor, outside the conductor field will be same, because outside the conductor there is air in both cases. So permeability of air is same in case both cases. So we are getting same field. Now here we are going to see this diagram very carefully. So in both magnetic and non-magnetic hollow conductors, now see, listen me carefully. In both magnetic and non-magnetic hollow conductors, the field strength is zero at the inner surface and increases to a maximum at the outer surface. Means here we are getting maximum field. Now see here we can consider F, then here F by 2, here F by 3, and F we are getting at a radius. And you see here 2R means 2 radius, and at 2R distance then we are getting field F by 2, means or if original field is 100, then at a 2 hour distance we are getting 50, like this. This is the calculation for if we are going away from conductor, our the magnetic field will be reduced, but reduced in this way. So in case of 2 hour, F by 2, in case of 3 hour, F by 3. Here, here R means radius of conductor. Now here magnetic conductor, as with both solid and hollow, and both magnetic and non-magnetic, the field strength outside the conductor diminishes with distance from the central conductor center. However, the difference between the permeability of magnetic and non-magnetic material affects the field strength within the conductor only. So suppose if we are using magnetic conductor, then field will be high only within the conductor, not outside the conductor, because outside the conductor field will depends upon permeability of air. So the whatever effect, that is only inside the conductor, because the low permeability of non-magnetic conductor, the field strength is relatively low, that is within the conductor. Okay, but outside the conductor field strength will be high. Now look here, this, see this figure very carefully. Now see, this is the conductor, and here we are getting less magnetic field. Why? Because this is non-magnetic conductor. But you see this is the idea of specimen, and we are getting maximum magnetic field. Why? Because there is because this outside job is having high permeability. If permeability is high, then magnetic field will be high. That's why we are getting this is high magnetic field here, because of permeability of the job. Because permeability of conductor is less, that's why less magnetic field. Permeability of this ring, this specimen is high, that's why we're getting high magnetic field. Since the magnetizing force is from the field external to the central conductor, it is obvious by comparing previous case that either a magnetic or non-magnetic bar could be used for central conductor. Means if you are using magnetic or non-magnetic, the field will not affect, because outside the conductor, in both cases, magnetic and non-magnetic, field will remain same. Then also why we are using non-magnetic, because of conductivity. Suppose if we are using copper bar, then conductivity is high. That's why we are easily pass the current through that bar. Otherwise, if we are using carbon steel bar, that because of conductivity is less and we are getting more resistance to current flow, that's why the bar will heated early as compared to copper bar. That's why generally we are using non-magnetic conductor, because copper conductivity properties. But regarding magnetic field, both magnetic and non-magnetic, magnetic field outside the conductor will be the same, because of this current carrying capacity, current carrying efficiency, we can say efficiency or we can say effectiveness, we are using copper as a conductor material. However, a material such as copper is often recommended as central conductor because there is less heat buildup due to better conductivity. Now here alternating current field distribution, and now see here this is the alternating current curve and this is direct current curve. And if suppose if we are giving current AC current, then what will be effect on magnetic field or on OD and outside. Similarly, we are going to do study on if we are giving DC, then what will be effect here. Now up to this point, all field distribution have assumed the use of direct current. Alternating current tend to flow near the surface of conductor. This phenomena is known as skin effect. Now see here, even if you are giving current at the center of conductor, then see the AC goes to outside immediately because of current tendency, and this tendency because of frequency of AC current. Okay, then see here again this is going uniformly, but one thing you see here carefully, the field strength outside the field, the field, where is the maximum field strength? On OD. And in both cases, in AC or DC, maximum field strength on OD only. Okay, on OD. And outside the conductor, see, again, there is only one graph for both current. So outside the conductor, the field strength will be remains same for AC and DC. Now here again we will discuss alternating current field distribution. AC provides a concentrated flux density near the surface, which provide for good detection of surface discontinuity. DC provides the best condition for locating subsurface discontinuities because of the distribution of flux density, because that flux density is distributed uniformly in case of DC. But in case of AC, your maximum current will flowing from surface on surface. So if maximum current density on surface, that means maximum magnetic field on surface. That's why we are AC is good for surface discontinuities and DC is good for near surface, or we can say subsurface, up to 6-7 millimeter we can say. Okay, then field strength outside the conductor is comparable for both AC and DC. Now see here this statement again important. The field strength outside the conductor is comparable for both AC and DC. As with a DC, both conductivity and permeability affect the field strength and distribution. Now see this ketose ring and this ring having this side drill holes at different depths. Let's consider this is the whole numbers and relative depth. This now this zero consider surface of ring, and this here this depth increases. Let's consider this is a 1 2 millimeter 1 millimeter depth. Then if we are going upside and this AC current AC weight is touching first time directly here. That's why if depth is less, depth of this continuity is on surface or near surface 1 to 2 millimeter, then AC is the best choice. But suppose our defect is 5 millimeter below the surface, means suppose this the 5 millimeter is here, then first one is touching here HWDC dry. So in case of depth is 5 millimeter, so which current is best? HWDC, and which take method? Dry method. HWDC dry, and see here current is only 200 amps. Even we can detect this defect with DC dry, but current value you see here more than 400 means, and we are using always less minimum current, not higher current. It's not necessary because wastage of current. So here we are using HWDC dry because we are detecting subsurface cracks with low current amount. And HWDC has a tendency of current flowing, stop. That's why we are getting little bit of particle dancing effect. Not like AC, but we are getting little bit. But it is more than DC. In DC, we are not getting the particle dancing effect. Okay, then with this quiz are here. You can solve this quiz, these questions, and also there is answers here. So in your free time, you can read these questions. If you have any doubt regarding any answer, regarding any question, you can feel free to write us. You can discuss with us. We are always ready. So on this address. So we at INDT, this is our mail ID, indtpune@gmail.com. So or you can visit to our website, www.iindt.co.in. So, and these are our contact numbers. So we are happy to assist you. Thank you.